Hi, welcome to AP Chemistry with Ms. Dalberg. Today we are working on gases free response questions, and let's start off with a 2004B question on hydrocarbons and gas laws. And so we want to know what the empirical formula of a hydrocarbon that contains 85.7% carbon by mass. In other words, we want to find what is the ratio of carbon to hydrogen in that compound. And so if we have 85.7% carbon, let's assume that we have 100 grams, and so we have 85.7 grams, which means our hydrogen is 14.3%, and so we have 14.3 grams. And so step one is to find the moles. If you want the mole ratio, find the moles. And so if we do that, we have 7.14 moles of carbon when we divide by the molar mass. And for hydrogen, we have 14.2 moles. And so the next step, and you might be able to do this without actually doing this step, we need the ratio. And you could probably see that it's a 1-to-2 ratio. But if these numbers were not easy to see, or if they weren't quite 1-to-2 ratios, it might be a little bit harder. But if you divide by the smallest, you get 1-to-2 as your ratio of carbon to hydrogen. So our empirical formula is CH2, which means we have a ratio of 1 carbon to 2 hydrogens, and these could be written in the opposite order. As long as the 2 is after the hydrogen, you are good. And points for this, you get 1 point for finding the moles, and you have to show your work, no point. 1 point for finding the ratio, and 1 point for the right answer. So part B tells us the density is 2 grams per liter. They give us the temperature and the pressure, and we want to know what's the molar mass. And so to find the molar mass, if we use our molar mass kitty cat equation, where you put your dirt over your P, if you're a good kitty cat, we have the density, we have the R, we have the temperature, and we have the pressure. And so we can substitute those values in, and when we do that, we'll find the molar mass. So if we take 2 grams per liter for the density that we're given, times our R value. Now, our R value, since we're in atmospheres, we have to use the R value with atmospheres in the units. So we have 0.08206 liter atmospheres per mole Kelvin. Now, the next step is temperature, and if you write 50 here, then you will get the wrong answer because it is in Celsius and you must convert it to Kelvin. And then divide by the pressure of 0.948 atmospheres. Things keep wanting to move around on me. And we get an answer of 56 grams per mole. If we look at our units, the 6 didn't quite come out. If we look at our units, our liters cancel, our atmospheres cancel, our temperature, and this is in Kelvin, cancels, and we're left with grams and moles as our unit. And so that is the unit of molar mass. So we have 56 grams per mole. Now, the last part says determine the molecular formula or the actual formula. So if we know the simplified empirical formula is CH2 and the mass of the non-simplified is 56 grams per mole, we can take the mass of this guy and figure out that factor by which it was simplified. And so if we take the mass of this, this is 12.01 plus 1.01 twice, and so we get 14.03. And so if we divide this by 14.03, we get a factor of 4. And so this was simplified by a factor of 4. So if we just multiply these numbers, the understood 1 and the 2, we get C4H8. Oh, let me go back. I didn't do points for the last two. So for B, you got 1 point for substitutions, and that includes things like converting the temperature, making sure you use the right R value, and then 1 point for the answer. And for this one, 1 point for the correct molecular formula. So we are 6 points into this question, and then we get to this one where we have two flasks connected by a stopcock right here, and this one contains a gas at 3 atmospheres, and this one contains a different gas at 0.55, and they're also different sizes. And so if we look at that, we are looking to calculate the total pressure of the system. So, but it's after the stopcock was open. And so the total pressure of the system, looking at this, you might be tempted to add the given pressures of the CH4 and the C2H6. But once we open that stopcock, the volume of our system changes, and when the volume changes, we know that the pressure is also going to change. So step one is calculating these two new pressures, and then we can just add them, like perhaps your initial inclination to just add those two pressures. So step one is to calculate the new pressure. And so we're going to use the combined gas law. And since the temperature, and right here, the temperature remained constant, we can say that P1 V1 equals P2 V2. And we can solve for pressure 2, and we get P1 V1 over V2 to give us our new pressure. And so we're going to do that twice. We're going to do that for both the CH4, this is the second pressure, and we can put in P1, which was for the CH4 3 atmospheres, and our original volume, which is 5 liters. Our new volume is after the stopcock's open, and we have 5 liters plus 1 liter for a total of 6 liters as our new volume. And so the pressure of our CH4 is 2.5 atmospheres. Now, if we want to find the P2 of our C2H6, we do the same thing. And so our original pressure, our P1, is, let me do that one in blue, is 0.55 atmospheres. And our original volume is only 1 liter. But our new volume, when we open the stopcock and have all of that, is 6 liters. So when we divide those two numbers, we get 0.092 atmospheres. So if we add those two up, our 2.5 plus our, actually, let's do it down there. We add these two together, we get 2.592 atmospheres, and when we convert to 2 sig figs, as we did in the other numbers, we get 2.6 atmospheres. Points on this, if you calculated either this one or this one, the final pressure of either one of them, you got 1 point. And if you found the total pressure, you got the second point. Part D, our last part of this problem. Now we're taking a hydrocarbon. We're given the density, the temperature, the volume, and we're told that it reacts with excess oxygen. So now we want to find the total number of moles of gaseous product formed. So if we want to know the moles formed, we have to figure out maybe how many moles of this we started with first. So if we know the number of moles we started with, we know the mole-to-mole ratio between the reactant in question, our limited reactant, and our products. So step 1 is find the moles, and step 2, convert to moles of the product. So step 1, to find the moles with the information that we're given. If we know a density, the temperature, the volume, and we don't really know anything else, if we had the pressure, we could do Pivnert, but we do not. So we are going to start with our density right here. And so looking at this density, this tells us how many grams we have of our reactant per milliliter. And we know how many milliliters we have. Now the temperature, like, it's nice that they give it to us, but we don't need to use that in this situation. So to find the moles of octane, if we start with our 7.03 grams per milliliter of octane, H18, if we know how many milliliters we have, then we can convert that. And so if we multiply this by 255 milliliters, we get 179 grams. So now if we take this number and start with 179 grams of C8H18, step 1 is to get it to moles. So I know how many grams are in 1 mole of octane. And if I add up the molar mass of my 8 carbons and my 18 hydrogens, I get 114. And so the next step, if I know how many moles of my octane I started with, I can figure out how many moles of product are formed. And so for every 2 moles of C8H18, I get that number from my coefficient. I know my mole-to-mole ratio. And normally we go to one or the other, but since they want all the products, the combined moles of products is 32. So every 2 moles of this produces, 34 moles of product. So The last step is to just multiply everything, and I get 26.7 moles. Okay. So using any of the conversion factors for density or mole-to-mole ratio or molar mass gets you 1 point. And you got 1 point for finding the moles of the product, or 2 points for this part D. Okay, now we're on 2002, and we have a rigid, aka the volume's not changing, 8.2 liter flask, which contains 2.5 moles of hydrogen, half a mole of oxygen, and some argon, but they don't give us how many moles. And they tell us the partial pressure of argon is 2 atmospheres, and the temperature is 127 degrees Celsius. So our part A asks us to find the total pressure in the flask, and we know that the total pressure equals the pressure of all of the individual pressures added together. So the pressure of hydrogen plus the pressure of oxygen plus the pressure of the argon. And so we know the pressure of the argon. We know this one. We do not know the pressure of either one of these, but we have the number of moles, we have the volume in liters, and we know the temperature. So our first step is to calculate the pressure of both the hydrogen and the oxygen. And so if we want the pressure, we will use, with our givens of volume, temperature, and moles, footnotes. And so when we find the pressure, we get nRT over V. And so if we're finding the pressure, let's do hydrogen first. We have 2.5 moles times R. Now the R that we need to use is, since we're working in atmospheres, and we can add them all up in atmospheres, we'll use the 0.08206 liter atmospheres per mole Kelvin. And our temperature is not 127, but it's 127 plus 273. So we have a temperature of 400 Kelvin, and our volume is 8.2. So when we get that number, we have 10 atmospheres in our container of hydrogen, and I'll do the same thing for the oxygen. So the oxygen, when we do the same thing, we have half a mole instead of 2.5, but everything else, since it's in the same container, is the same. We use the same R. We use the same temperature. They're both at 400 Kelvin, and 8.2 liters. And so when we do that one, we get 2 atmospheres. And so if this is 10, and this is 2, and this is 2, we get a total of 14, and this should have 3 sig figs. So I'm going to go ahead and add a 0 after the decimal, but we have 14 atmospheres. So points on this, you got 1 point for finding the pressure, the partial pressure of hydrogen. You got 1 point for finding the partial pressure of oxygen, and then you have found you got 1 point for adding them together to get the total pressure. The next part says calculate the mole fraction of hydrogen in the flask. So to calculate the mole fraction, you take the moles of hydrogen divided by the total moles. In other words, the moles of hydrogen plus the moles of oxygen plus the moles of argon. Now, we know the moles of hydrogen, it's given, 2.5. And so, we can write that in. We know the moles of oxygen, 0.5. And, get back. So, we have 2.5 plus 0.5, but we do not know the moles of argon. This is our unknown. We don't know it, so now we have to find it. So what we do know the volume, we do know the partial pressure of argon, we know the temperature in the flask. So to find the number of moles, if we use PIVNERT, see, things keep wanting to move around on me. And so if we solve for moles, we end up getting PV over RT. And our pressure of argon is 2 atmospheres. That's our partial pressure of the argon. Our volume is that 8.2 liter. That's the size of the flask. Our R, since we're in atmospheres for everything else, we're going to do our liter atmospheres per mole Kelvin, R value, and 400 Kelvin for our temperature. And so when we multiply that, we find that we have half a mole of argon. And that should actually be three sig figs. So we can add our half a mole. Everything wants to move around today. Okay, so we took this number and plugged it in for our moles of argon in our mole fraction equation. And when we add them up and divide, we get 0.714 as our mole fraction. So we got 1 point on this one for finding the moles of argon and 1 point for finding the mole fraction. Our next step tells us to find the density of the mixture in the flask. Okay. So to find the density is mass over the volume. And we know the volume. We know this one. We know it's 8.2 liters, but we do not know the mass. But we can easily find the mass of each of those substances. For example, for hydrogen, we know that there are 2.5 moles of hydrogen. And so to find the mass, we can just multiply by the molar mass, because we know for every 1 mole of hydrogen gas, we have 2.016 or 2.2 grams. And so we have a total of 5.04 grams of hydrogen in that flask. And we can do the same thing for oxygen. For oxygen, if we have half a mole, and that's 0.5 moles. If we divide by the molar mass, or multiply by the molar mass, for every 1 mole of oxygen, we have 32 grams. And so for oxygen, we get 16 grams. And for our last one, our argon, we found in a previous section, we have 0.5 moles. And we know for every 1 mole of argon, there's 40 grams. And so we have 20 grams, 20.0 grams of argon. So if density is mass divided by the volume, the mass of this system is the sum of all of those, 5.04 plus the 16 plus 20 over our 8.2 liters, and we get 5 grams per liter. And if we look back at everything, we should have 3 sig figs, and the units are grams per liter. So we'll fix that, make that a little neater. 5 grams per liter. So for this one, we have 1 point for finding all of the masses. So if you found all 3 masses, that was worth 1 point. And 1 point for calculating the density. Okay, now we're saying that that mixture is ignited by a spark, and we have this reaction going on, hydrogen reacting with oxygen to form water. It says give the mole fraction of all species present in the flask at the end of the reaction. Okay. So that means we have to figure out what's in the flask. So if we want to know what's in the flask, we could have all of these, right? Except we know that one of them is going to be our limiting reactant, one of them is going to be our excess reactant, and one of these, argon, is not going to react at all. So if we look at the hydrogen, if we started with 2.5 moles of hydrogen gas, and we started with 0.5 moles of oxygen gas, we can look at that and maybe kind of tell which one's our limiting reactant. And since they're in a 2-to-1 ratio, we know that oxygen is going to be our limiting reactant. We will have no more oxygen left, because for every 0.15 moles of oxygen that react, 1 is 0.5 times 2, 1 mole of H2 will react. And so if half a mole of this reacts, we're only going to form 1 mole of water. And so this we can do an ice chart, and I know we haven't talked about that in class, but here is our initial conditions. Then we have our change, and then we have E is for at equilibrium, and this guy kind of goes to completion. All of one of the reactants, the limiting reactant, is consumed. And because the molar ratios are kind of easy, I think we're going to attempt this one. So initially we have 2.5 moles of our hydrogen, we have half a mole of oxygen, and we have 0 water. Now the change is we're going to use up our reactants. And so we're going to use up 0.5 moles of our oxygen. All of that will be gone because that's our limiting reactant. If this reacts in a 1-to-2 ratio, we're going to use up 1 mole of hydrogen, and we're going to form 1 mole of H2O. And so at the end, when we add this up, if we have 2.5 moles that we started with of our excess reactant and we only used up 1 mole, we're going to have 1.5 moles of that left over. We're going to have 0 oxygen left over, and we're only going to form 1 mole of water. The other thing in our container is our argon. And argon, we started with 0.5 moles. It was there. Argon is not involved in the reaction, so after the reaction, we will still have 0.5 moles of argon. And so to find the mole fraction of everything, oxygen is the easiest. Oxygen, it's 0. Everything else we have to calculate. And so if we look at hydrogen, if we want to find the mole fraction of hydrogen, we need the number of moles of hydrogen divided by the total moles. And so hydrogen, we have 1.5 moles left. Our total moles, if we add up the hydrogen, the water, and the argon, we have a total of 3 moles. And so for our hydrogen, we have a mole fraction of 0.5. Now, if we look at sig figs from the starting point, our starting information, we should have 3 sig figs there. And so this is our mole fraction for hydrogen. Our next one that we'll do is oxygen. I'm sorry, we already did oxygen. We have none left. Let's do water next, H2O. And at the end, we said we had 1 mole of water, and our total is 3. So we have 0.333. And for argon, we have our We have our 0.5 moles divided by 3, which gives us 0.167 moles for the argon. Ooh. Okay. Points on this, you have 1 point for calculating the moles of water. And so if you found the moles of water right here or right here, if you found the moles of water, that was 1 point. If you found the total moles, so you took all of the moles and added them up, and you found the total moles, I'll do that in purple, and found the total to be 3, that was the second point. And then the last point for this, you got 1 point for any 2 mole fractions, excluding oxygen. So no point for finding oxygen, but if you found 2 of these 3, you got 1 point. And I guess a lot of people forgot about argon, finding a mole fraction, so they didn't take off for that, as long as they included it in the total moles.